In this problem, we have a particle of mass m, which is constrained to be moving along a smooth horizontal top of a table. There's a cable that's attached to that. The cable is fed through a hole in the table. And someone is applying this force T to the other end. We know that the particle, as a result of this applied force T, which is not a constant, as a result of that, the particle takes on an elliptical path, given by this equation here of x squared over 9 plus y squared over 36 is equal to 1. We know that at position A, the speed, and once the particle moves to B, we want to find what tension that it takes in order for it to be at position B. Again, the particle moves on an elliptical path. I've shown a sketch of that here, as well as the positions there for A and B. So the observation that we make from our FBD is that the force T acting on the particle of mass always acts toward O. So then in anticipation of using the angular impulse momentum equation, we can use the fact that the summation of moments about O, since T passes through O, will say that the angular momentum of that particle as it moves on its elliptical path is one where H about O is a constant. H about O is a constant. So whatever H about O is for A has to be the same thing there for B. About A, it's just mr cross V, where the R vector goes from O to A. So from O to A, we said that that was a distance of 3. That's in the I. A is moving in the J direction. I cross J is a K, so this is 3 mVAK. When the particle is at B, it's the same kind of expression, mRB with respect to O, cross with the velocity of B. So B is on the y-axis a distance of 6 from O. At point B, the particle is moving in the negative x direction with some speed of VB, which we need to find. J cross I is a minus K, so a minus and a minus makes this a 6 mVBK. Conservation of angular momentum, H at point A must be equal to H about O for point B. So this says then that 3 mVA is equal to 6 mVB. So the speed at B then is equal to half of the speed of what it had at position A. So that tells us how fast that B moves. What we want to do is find the tension. So tension is best found from Newton, because that's where forces in accelerations are related to each other. So we're going to use a Newton formulation. And what we will do is sum forces, and this is at B, we'll sum forces in the x direction. Well, we see that there are none. So that's m times x double dot. Summation of forces in y, we see we got a minus tension force, and that's equal to my double dot. So this is where we actually use the shape of the path in order to calculate what x double dot and y double dot are. I guess this is clear that x double dot is a 0. But what we need to do is find y double dot. So our equation, again, was x squared over 9 plus y squared over 36. That was equal to 1. I use implicit differentiation. I'm going to get a 2x x dot divided by 9 plus a 2y y dot over 36 is equal to a 0. The 2's, of course, will cancel out those, and I get a 4 over here. I take one more time derivative, and that becomes a 4 times x dot. The time derivative of that is x dot squared plus x double dot. The time derivative of y dot is going to be a y dot squared plus y double dot, and that is a 0. So what we see from here is that from above we had x double dot is a 0. We also know that from this equation here that y dot is a 0, which happens because x is a 0. This is at point B. So we strike out this, and what we find out is that the thing that we need, which is y double dot is equal to minus 4x dot squared divided by y, and so that's equal to minus 4 times x dot, that's VB squared, divided by y, which at this position is 6. So that ends up being, I guess, minus 2/3, one more step. VB is equal to VA divided by 2 squared. So y double dot is a minus VA squared divided by 6. So from our y component of our Newton's second law equation, we see that T, which is equal to minus my double dot, is equal to mVA squared divided by 6. And that is the tension in the cable at B, the applied force T. So the primary focus of this problem is to use the conservation of angular momentum, or I should say the angular impulse momentum equation, to figure out what the speed is at B. We know what it is at A, and the thing must move under the central force there of T in such a way that the angular momentum about O is a constant. That's where we found out that VB was half of VA. Then we used Newton's second law in order to get the force acceleration equation required to find T. We used implicit differentiation twice to be able to solve for y double dot, and from the y component equation that gave us T.